let us look at the use of a finite element program for doing the patch test and other practical problems that we had discussed in the previous class. One of the patch tests that we performed was on this type of a mesh that is consisting of totally 9 nodes and 4 elements, each of 4 node type quadrilaterals. And what is done is we applied a pressure loading on both the right hand side and the left hand side, and then just given some boundary conditions that will prevent any rigid body modes of deformation. And to prevent the rigid body motions, we had fixed node 1 on a hinge, so that both x and y direction displacement is constrained. Then at node 2, it is on a smooth roller, so that the material can move in the vertical direction, but not in the horizontal direction. And then on the right hand side, a pressure loading of 100 is given, and each of these is of length 2 units. And let me just indicate the units here. This is of length 2, and this is of length 3, and this is of length 1 and 3, right. And so, if you apply a pressure loading of 100 kPa here, and because this being a 2 node surface, the load is equally distributed. So, 100 times 2 is 200. So, you will have 100 here and then another 100 here, and then on the same for the same pressure on the other element 4, you will have 100 here and 100. So, at node 8, you will have totally 100 plus 100 200, and then on this surface also we have given the loading in the other direction like this. Okay. And so, if and then this element 1, both of these nodes are fixed in this lateral direction. So, there is no force, and there is only force on element 2, and this pressure of 100 is acting on a length of 3. So, it is totally 300, and we distribute half of that, that is 150 here at node 3 and another 150 at node 2, but node 2 being a fixed node will not have any load transferred there. Okay. And then the same test is repeated by sorry, I think oops, sorry. So, the same test is repeated for by changing this element into a 5 node element. I have introduced another node 10, and then this will be a 5 node element. The nodes are defined as 6, 3, 2, 5 and 10, and that we will see in the GEOFEM program. And here also we have this loading of 100, 200, 100, then 150. And now let us see how we do this in the program. And okay, let me just see where is my data files. Okay, patch 1, right. Okay. So, here is our data file for the patch test. Let me just zoom it a little. I'm not able to, I don't know why it's not, sorry, I am not able to zoom it, but let me just illustrate this a little bit. Oops, what happened? Okay, I cannot use the pen. It's okay, I think we will do it. Okay. So, here this see, this mesh has 9 nodes, and then I have made all the 9 nodes free, but then later I have given some boundary conditions, and the loading I have given instead of point loads, I have given it as a uniform pressure, so that the program can calculate. So, on both the right hand side surface, on the right hand side surfaces, I have applied a pressure loading of 100. On the left hand side at node 3, there is a load of 150 applied, okay. And then we have all these quadrilateral elements, they are defined with 4 nodes, 1 5 2 1 4, then 6 3 2 5, 8 5 4 7, 9 6 5 8, and then node 1 is fixed in both x direction and y direction. So, you see here 1 and 2, it is fixed, whereas node 2 is fixed only in direction 1, that is in the x direction. Okay. And so, if you look at this result, let me see whether I can, okay, yeah, I think I can increase the font a little bit. Okay. Let me increase it a little bit more. Okay. So, here we have a mesh with 9 nodes, and then number of element types is 1, because the entire mesh is made up of only continuum elements. Then there are no body forces considered. Analysis type is only linear elastic, 0, and then these are the 9 nodes, and then the coordinates, and all the displacements are free at the element level, but then later we put some constraints, and this is a plane stress state, the Young's modulus, Poisson's ratio, and then there are 4 elements. The first element is connected between nodes 5 2 1 4, second, third and fourth, and then there is one parameter IRCT that refers to the shape of the element. If this value is 0, then it tells the program that the element is a triangular element, and if it is given as 1, it is a quadrilateral element. Then there is another type 2 that refers to the infinite element. Then integration order, 1 is for 1 point, 2 is for 2 points, 2 points in each direction, both xi and eta directions, and then the stress grouping is actually, if you want to print the stresses at some points, you can use this option. And then the loading at node 1, there is a load of 150 given in the negative x direction, because the L code is 1. Okay. And then on the right hand side, we have the nodes. There are 2 surfaces, one is 7 8, 8 9, and then I have given a negative pressure. So, as you recall, if it is a positive pressure, it will be acting into the element, and now on the right hand side, I want the pressure to act outwards. So, I have given that as a negative. Okay. And then if you look at this, we have 4 elements, and all the elements, they have a tensile stress of 100 everywhere. Okay. And there is no sigma y and no sigma xy, and these are all zeros only. 10 to the power of minus 30 means practically 0. Then the sigma x is 100, exactly 100, that is what we applied. So, we can say that this particular patch of elements is able to pass the patch test, because we applied a constant stress of 100, and the same thing is predicted inside the elements. Okay. So, we can say that this particular patch has passed the patch test, and one of the requirements is that we should apply boundary conditions corresponding to help the patch to develop the constant stress state. And now, let us do slightly different thing. Let us prevent the mesh from moving in the other direction by putting one more boundary condition. So, here I am just doing one more thing at node 2. So, at node 2 I am fixing the displacement in the y direction, and now let us see what happens. So, here we are not allowing the mesh to deform in the other direction. So, now we see our sigma x is not constant, it is nearly constant. So, it is within element 1 at one integration point 103.56, another point 98.7, 99, and actually if you are away from the boundary, is actually element 1 is very near to the boundary, and so that got affected very badly in terms of the varying stresses. But if you take element 3, that is away from the boundary, the stresses at all the 4 points are nearly the same, 99.19, 99, 100, 100. Okay. And then you see here we did not apply any stress in the y direction, but then because of the Poisson's effect there is some stress developed, because we are not allowing the material to freely deform in the other direction. And the same thing, although we did not apply any shear stress, the material has developed some shear stress, whereas in the previous case, let me open this and show you. Oops. So, this is our previous result, where we allowed the lateral deformations to take place, so that the Poisson's effect will not be seen on the strains and stresses. So, we have a perfectly sigma x is 100, there is no y sigma y stress, and there is no shear stress in all the elements. Okay. Whereas in this new case, where we prevented the material from straining in the other direction, we have a problem. Okay. So, when we perform the patch test, we must make sure that your boundary conditions also they enable the patch to pass the patch test. Okay. That is very important. And then the same thing if you do for the element with 5 nodes, we see that see one of the elements 2, it has 5 nodes 6, 3, 2, 5, 10, and then everything else is the same, and all the stresses inside the elements are all constant, 100 in element 1, 100 in element 2, 3 and 4, and there is no stress in the sigma y direction or tau x y. So, we can say that even a combination of 4 node and 5 node quadrilateral elements is able to pass the patch test. So, we should expect the monotonic convergence by using this type of elements. Okay. And in the previous class, we had also seen the influence of the type of element and then the order of integration. And so, this particular one is from the textbook by Cook, Malkus and Plisha, where the influence of the type of element 8 node quadrilateral or 9 node quadrilateral, and then the whether if you have a rectangular element or a distorted element, what difference it makes. This particular one is a perfect rectangular element. This is a distorted element, but with a straight side, and the third one is a distorted one with a curved side. Okay, curved and for the first one, both 8 node and 9 node element meshes they are able to give a very good result with reduced integration, 2 by 2 integration, and when we use higher order of integration 3 by 3, the solution accuracy has reduced a little bit, especially in the sigma x. Sigma x is at this point at one of the integration points, and then when we distort the element, the 8 node element has performed very badly. When you have 2 by 2 integration, the displacement is only 36% of the actual result, and if you use a higher order of integration 3 by 3, is even worse, 0.161, and the same thing when you have this curved edge, the solution is very bad. But then if you have this 9 node element with a 2 point integration, it is it's not bad. Okay. And let us see this. Okay. So, this is the analysis with sorry, I think this is 8 node or 9 node. Let me open the 8 node. Okay. So, this is the one with 8 node quadrilateral element. There are totally 13 nodes. So, here we have 2 elements and 13 nodes 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Okay. And oops. I think yeah. Okay. This the 13 nodes, and then this is the deformed shape. The yellow one is the original mesh, and then this black color one is the deformed shape. And let us see how the displacements and everything are predicted. Okay. So, the first one is 8 node element. There are totally 30 nodes, and nodes 1, 2, 3 are fixed completely because we have a fixed end cantilever, and then 8 node elements. The element 1 is connected between these nodes 6, 1, 3, 8, 4, 2, 5, 7. Then second element is 11, 6, 8, 13, 9, 7, 10, 12 and so on, and then the shear load of 100 is applied at the tip, and the tip displacement should be 0.02 but we are getting a reasonably good value like 0.019. And then if you look at this horizontal deformations, the center point there is no horizontal deformation because that is a neutral point. See, within a depth of 10, I think this depth is 10. Yes. So, this the depth of the beam is 10 and the length is 100 units. So, at mid depth there is no lateral deformation. So, that means that it has undergone a pure flexural type deformation, and the upper surface has deformed to the left by 0.0014, and then the lower surface has deformed to the right by the same amount 0.0014. So, the total is 0.0028. That is the relative deformation divided by 10 is 0.00028. And if you look at the theoretical solution, see this theta is 3 times 10 to the power of minus 4, and our finite element is predicting 2.8 times 10 to the power of minus 4, and which is not bad, considering that we have considered only 2 elements. And then and then let us look at the stresses. See, the stress sigma x is our flexural stress, and that is the maximum value is 6000. I think that is given in the PowerPoint. The flexural stress is m by I times y bar. At the fixed end your moment is 1000 times 100. 100 is the length, 1000 is the total shear load divided by I 1/12 10 cube, and the maximum the distance of the fiber from the neutral axis is 5, that is 6000, and that is what we see here. So, at the fixed end when x is 0, our sigma x is 6000, and the upper fiber is actually it's bending in the anti-clockwise direction. So, the upper surface is on the compression. So, we have minus 6000, and then the lower surface is plus 6000, it is tensile stress. And then if you see this at the tip when x is equal to 100, our bending stress is 0 because that is the free end, and then our at mid length at x of 5, both element 1 and element 2 they are giving the same stress of 3000, depending on whether you are at the top it is a minus 3000, and if you are at the bottom it is 3000. Okay. And then although we did not apply any stress in the y direction, there will be some sigma y. There is a formula for that, and if you check these values are not bad, sigma y. Then sigma xy, we applied a shear stress of 100, but then we are not able to predict that shear stress well, maybe because of this we have used only 2 elements, and so it is not able to predict the shear stress correctly, but if it is done correctly then it should have predicted exactly 100. Okay. And then let me show you another result with 9 node element. See, with 9 node element mesh, this is with 3 point integration. Our displacement is at the tip is 0.02, that is not bad. It is, but then our flexural stress is not predicted correctly. It is at x of 0 we are getting only 5389 against a stress of 6000. That is because of our integration order, whereas with the 8 node element we were able to get the exact flexural stress of 6000. So, you see that our results not only depend on the type of element, but also on the order of integration. We have to repeat and see whether we are getting reasonable results or not. Okay. So, now let me just show you quickly two other things. So, imagine that you have a thick cylinder and that is subjected to internal pressure, and in one of the classes before we have seen that there can be two different models. One is a plane strain model by taking a section across the length. We can take we can model it as a plane strain case, and this full circle, this full cylinder is modeled in with the quarter symmetry, and see here along the x axis all the nodes are moving only in the x direction, whereas on the vertical boundary at mid section you have only vertical displacements, and then the same thing we can model by taking a longitudinal section as an axisymmetric one, and so the axisymmetric one we have taken one thickness and of unit length, and constrained all the lateral displacements so that the cylinder can move only in the along the radial direction like this. So, here you see all these nodes with a circle. So, that means that they cannot move in the vertical direction, but they can only move in the horizontal direction, and this is the radial stress with axisymmetric mesh. The maximum at the interior point is 12.8. Then as you go away the pressure reduces, and sigma y, that is actually in the other direction, longitudinal direction, it is it's actually it is very small, because there is not much that acts along the length, and it is constant along the across the thickness, it is constant. And sigma transverse, that is the hoop stress or circumferential stress. This is also the maximum is somewhere around 22, and it is reducing as you go away. And this is the sigma x with the plane strain model. It is also predicting almost the same. The maximum is 12.32, then it is reducing, and this is sigma z. Sigma z in the plane strain model is equal to your sigma theta in the axisymmetric model. It is about 22 at the interior. Is actually this is one of the integration points. This is not exactly at the tip. I will show you where the stresses are computed, and okay. Let me just go back. So, this is our mesh that we have used for this analysis. Let me node number, okay, and then let me show you the boundary conditions. Okay. Okay. So, this is our mesh. Actually ignore these straight edges. Actually this post processor does not have the capacity to draw curved lines, it is just simply drawing straight lines between all the points. But inside the finite element program, it is a pure isoparametric element. So, it will consider as a curved surface, and so we have totally 12 elements, and then these are all the nodal points, and let us see how the stresses have varied. Let me plot sigma x. We can select the integration points. See, these are all the oops. Let me just sorry, I think. Okay. So, these are all the points where the stresses are computed. These are the integration points, and we can draw a line and then select all these points and then plot any stress, and here plotting the sigma x. I think it has not done it correctly because it is starting from 129. It should have started from 103. Let me just do it again. Sorry, I think because actually I think there is a problem because I'm displaying the okay. So, now let me select at some other along some other line. Okay. So, here it's showing the sigma x variation along the length, and somehow I am not able to select the points because our inner radius is 100 and outer radius is 200. It is able to select the outer radius points, but not the inner radius points, I think because of the accuracy of this system, I think, but it is able to do it on my laptop. Okay. So, if you have a problem whether you have a plane strain model or axisymmetric model, we see that we get the same result. In fact, you can compare the displacements and then the stresses and strains from both the plane strain and axisymmetric models, and you will see that there is no difference. So, that means that whatever we have done is accurate, and then we can compare these with theoretical results. In most of the elasticity textbooks, we have the solutions for thick cylinder subjected to internal pressure, okay. And that I am not doing here, but I will give it as a handout. You can refer to the handouts that are uploaded on the website. Okay. So, this is some introduction how you can use the finite element program GEOFEM for doing our class tests, class problems of the patch test, and then the other problems like the cantilever beam and then the thick cylinder. I will give you more instructions on how you can use these programs and then do this analysis, so that you can do your weekly homeworks. Okay.